So this is Jack Jackson. In this video we're going to talk about integration by parts. Now integration by parts is a substitution technique that is made possible by reversing the product rule for derivatives. Now in an earlier video we proved the integration by parts rule. And that rule is the integral of u dv equals uv minus the integral of v du. V and u are both functions of x, and by dv we mean the derivative of v with respect to x times dx. So it's dv over dx times dx. And of course by du, as usual, we mean the derivative of u with respect to x times dx. So we've made a substitution, a u and dv. So what you really do is you take your original integrand, you rewrite it into two parts. You split it into two parts that are multiplied together. Okay, there's your product, u and dv. So one part is u, one part is dv. The part that's u, you have to find the derivative of to find du. This is just like we normally do in a regular substitution. But on the dv part, which will always include the dx, that part you have to find an antiderivative of to get v. Now, notice that the dv part has to be something that you already know how to take the antiderivative of. So that right there limits what you can substitute for the dv part. And if you do get this to work out and get a u and a dv substitute in here, you'll find out, of course you'll have the u, you'll have to find out v by doing an antiderivative of dv, and so that you just get u times v, minus another integral v du, and again the v is the same v as here, which is the antiderivative of dv, and of course the du is the derivative of the u. And the hope is that this second integral here on the right side is easier to find, or that antiderivative is easier to find than the first one. Okay, now that may sound a little confusing, but let's do an example here. Okay, so here we have x times e to the 9x. Now the first thing, we might let u be 9x, and then du is 5. Okay, or is 9, and the 9 gives us no problem. We can put the 9 with the dx, but the problem is, see, we still have this x out here. And so if that x wasn't there, this would be a straightforward, easy substitution, standard substitution kind of problem. Okay, but that x is there. So we kind of like to get rid of that if there was some way to do it. So our basic substitution technique does not work, so we have to move on to the next thing we might try is integration by parts. Now, I consider integration by parts a basic substitution, or a basic derivative, or excuse me, integral technique, a basic integration technique. But I think of it as the most advanced of the basic techniques. There are other people who would consider it the easiest of the advanced techniques, and so sometimes you'll see integration by parts in a chapter that starts going through the more advanced techniques. But I make sure I cover this in first courses like Survey of Calculus and Calculus 1, because I think it's just the product rule backwards. Product rule is one of our basic derivative rules. And so that makes integration by parts a basic rule, and also has some very nice applications. So let's see how this works in this case. Now notice what do we have here. We have a polynomial part, an x, and then we have an exponential part. You basically have two options here. If we either have to let the e to the 9x go with the dv, or we have to let the x go with the u, or we let it go the other way around. Well, look what would happen if we let the x go over here with dv. If we had dv as x dx, then when you took an antiderivative, you'd be 1/2 x squared. And this integral down here would be even worse than what started with, because it would now have an x squared. We were trying to get rid of that x. Now, e to the u basically doesn't get any, or e to some power, let's say w. E to the w doesn't get any better or worse when you take a derivative or integral. So you could put it on either side. So given that choice, we'll let the exponential go with the dv, and we'll put the polynomial part over here with the u. So that's sort of our standard rule. If you have a polynomial times an exponential, let u be the polynomial part, and let the exponential part go with the dv. Now, I want to set dv up exactly so that I get a v that's really nice. So if I do e to the 9x times 9 dx, that's e to the w dw, where w is 9x, then the antiderivative is, that's just the antiderivative of e to the w dw, which is e to the w, or e to the 9x. Now, if I'm going to put a 9 in there, then I need to put a 1/9 here, and I'm going to include that as part of the u part, which is the 1/9 x. Now, notice that the dv always has the dx with it, and you're taking an antiderivative over here on this part, whereas you're taking a derivative here. Okay? Notice you're going forwards and backwards in terms of derivatives here in the same part, so you have to be careful, and the same problem, so you have to get each part going the right way. The dv is the part you take an antiderivative of, and the u is the part that you take the derivative of. So du then is 1/9 dx. So with that substitution, the 1/9 x that we have here times this, the 9's cancel, we're back to where we started, so that's legal. And by grouping them this way, the 1/9 x is u, and the e to the 9x 9 dx is dv. So we do have the integral of u dv. So that's exactly set up to do integration by parts, the product rule backwards. And so what we get is uv minus the integral of v du. Substitute back in, uv, that's the product of these two here. So 1/9 x times e to the 9x, minus, that does have a minus there, subtraction, the integral of v du. So where's v? V is e to the 9x, du is 1/9 dx. Now if I'll take I need to stick a 9 in here, and a 1/9 times that 1/9 is 1/81, pull it out front. Now I've got e to the w dw just like I had before. So here I've explicitly written it out, but that's the same integral we've already done, that same antiderivative we did up here. And so of course that is just e to the w. I still got my minus 1/81. When the last integral sign disappears, that's when you put your plus c, and you only need one plus c. Okay? Now substitute back in, w is 9x, and there's the answer. And I'm just going to clean it up a little bit. I'm going to factor out a 1/81 and an e to the 9x. So if I'm dividing by 1/81, it's the same as multiplying this by 81. 81 times 1/9 is 9. And these cancel by dividing them out, it leaves me an x there, 9x. 81 times this minus 81 is -1, and then e to the 9x cancels, so that's just 1 there. And then the plus c is outside of all that. So here is how I would write the final answer, is 1/81 times e to the 9x times 9x plus 1 plus c. Okay? What if we were to check this? Let's go ahead and check it. I don't have that typed up yet, so let me go ahead and copy that. I don't think I have it checked. Okay. So what I want to notice is this. Okay. Notice that excuse me. Notice that the check of a problem by parts will always use the product rule. So here's our check here. I just copy this because I just want to get my hands on the function here. Now what I should see, if this checks out correctly, is the derivative of this guy should equal, ultimately, this part right here that we started with. So this is what we should say. I've got the beginning and ending of it. So I probably shouldn't delete all this because some of this same stuff will end up showing up here. So that's what we want to show. Now, of course, the easy part is we always get the plus 0 at the end, right, for the derivative of the c part. Okay, now what do we have here? Well, here we have, sure enough, the product rule. Okay, actually, I'm going to go ahead and use the constant multiple rule there, and then say we have the derivative of this part right here. Okay, so I use the sum rule and the constant multiple rule and the derivative of a constant. Okay, now what does this give us? Well, let's see. Let me put another parentheses here, which is this parentheses. Now this derivative here, let me do a little copy and paste here. It's the first part times the derivative of the second, something like that, plus the second part times the derivative of the first. Okay, that looks good. And I can drop the plus 0. Alright, let's see what that gives us. Okay, the derivative of 9x minus 1 is just 9. Where'd the d over dx go? Well, we did it. We did that derivative, so it's gone. This is derivative of e to the w with the same substitution I had before, which is e to the w. And then just times the derivative of the 9x, which is just, I'm just going to go ahead and write 9 there. Okay. Now let's see what we can do with this. Let me go ahead and see what we can do with some of this. Well, the first thing I'm going to do here is this. I'm going to factor this 9 out, so I can bring that 9 and that 9 out to the front. With this 1 over 81, it becomes 1 over 9. Okay, and I can also factor out this e to the 9x, which leaves a 1 here and a 1 here. Okay. And then what comes next? Well, this 1 and that negative 1 cancel, so that only leaves a 9x here. Get the rest here. And then the 1/9 and the 9 cancel, and if I want, I can bring the x in the front, and sure enough, we get what we started with. And so that proves that we did the right thing. So there's our check. Now that's our, of course, that's our check with the with no technology. How about a technology check while we're at it? Get my calculator going here. Okay. Let's just turn it off. That's big enough. Okay, and what do? Now, for a derivative problem, we check a different way than we do an antiderivative. So, we basically check it the way we're going to do this. So we take the final answer here, which is 1 over 81 parentheses. Actually, I can draw. Well, yeah, why not? Let's put parentheses around the 1 over 81. And then that's times e to the power, parentheses, oops, where's the e to the power go? Start over again. Parentheses, 1 over 81, there we go, e to the power is 9x, close the power, open parentheses, 9x minus 1. And you can put plus, any number you want there, or just leave that out. Put any number you want. Put 9, put 7, put 15, put whatever number you like there. Put 0 there. Just leave it off if you want. It doesn't matter. because here we're going to put the derivative. Now, I think I've got the older operating system on this one, so it's Math 9, no, Math 8, there we go, Math 8, and we take the numerical derivative of y1, that's variables, right arrow to y variables, function, y1, comma, x. If you'd like to put a comma, some small value for delta x there, you can, or h there, you can. So that's a numerical derivative. And actually, I don't need to see the table for y1, but I do need to see the table for y2. So you put your answer in y1, and you put the original function, x times e to the 9x. We put that in y3. Now, if we've done this correctly, the tables for y2 and y3 should match some kind of automatic table. It really doesn't matter what we're looking at, that's fine. And look at that, they match. Now, when I say they match, sometimes you get down here, for example, here you may see some changes in the digits way over here because these are approximation techniques. Actually, the y2 is an well, they're both approximations. y3 is the better approximation, which actually takes our final, our original function, I guess it is here, and actually x e to the 9x and puts in numbers and approximate. y2 is doing a numerical derivative of our answer, and those are not necessarily the same. In fact, this one looks a little different. That's 0. This is 3e negative 6. That means 3 times 10 to the negative 6. That's 0.5 zeros and a 3. Well, again, to many decimal places, these are the same, so it is in fact checking out. So let's just, while we're at it, let's just show the check there numerically. Actually, I don't want it there. I want it down here where we did the check. Something like that. And let me just format this just a teeny bit before we move on. Maybe give these guys a little bit of a border. And there's our check. Okay. I may clean that up just a bit. Let me do something else here. Okay, there with a little moving stuff around, I've got the formal by hand check here, and then the approximation calculator check over here. And either way, we do see it is checking out. Okay, so that's how integration by parts works. Now let's see if we can maybe do another one. Okay, one of the things that you may notice about our basic families of functions that we know how to do derivatives of, well, we have lots of those, and one of the basic ones was the derivative of the logarithm. But when we look at our families of basic functions that we know how to do antiderivatives of, it turns out that the logarithm one was not in our basic list. We can develop a formula for the antiderivative of logarithm, but we're going to do it by integration by parts. Now, if we knew how to do the antiderivative log of x, then we'd be done, right? So it's obviously not going to be part of the dv. We don't know how to do the antiderivative of it yet. It'll be the part that's the u, and the dv is simply dx. And of course, if dv is dx, that makes v equal to x. Now, if u is natural log of x, du is 1 over x dx. Well, with this substitution, we see that log of x is u, dx is dv, and we have the integral of u dv. According to parts, then that is uv minus the integral of v du. Now, uv is, let's see, u times v. Well, that's log of x times x minus the integral of v du. Now, look what happens here. The v is x, the du is 1 over x dx. This x and 1 over x cancels, and now we just have the antiderivative of 1 dx. And so we get 1x here, minus comes down from there. And then of course now my last integral sign disappeared, so I put my plus c. And if I want, I can factor out an x. And this is x times ln of x minus 1 plus c. So if you want to memorize that as a basic rule for logarithms, you can, or you can just maybe more easily remember that you just do that you can find it by integration by parts. So once again, here's a check, and this we will always end up using the product rule in our check. So let's check this out. The derivative of x times log of x minus x. First of all, it's three derivatives. The derivative of c is 0. The derivative of minus x here is negative 1. And the derivative of x log x is the product rule. X times the derivative of log x plus log x times the derivative of x. Somewhere in this process, you're going to be using the product rule if you did integration by parts, because it is the product rule backwards. The derivative of ln of x is 1 over x. The derivative of x is just 1. And let's see what happens here. X times 1 over x is 1. That cancels with this minus 1. And sure enough, we're right back at ln of x. Notice ln of x is only defined for positive numbers. So our answer should only be defined for positives, but it also has an ln of x in it as well, so that is also going to limit it to only positive numbers. Okay, so let's keep going here and do one more example at least before we stop and maybe switch to another video. If you have a product of well, let's back up just a minute. In this example where we had the product of a polynomial and an exponential, the exponential, whether you're doing derivatives or integrals, pretty much stays an exponential the whole time. But if you have a polynomial, every time you do a derivative, the power goes down 1. So it was nice to let the polynomial be the u part when we can, and the du sort of gets better in the sense that it goes down 1 a degree. Now this time we're not going to be able to do that because we can't let the u be the 5x because we put the log x over here. It's not one of our basic products. Now we could of course use the rule we just derived, but without using that, we're not going to let the logarithm be part of the dv. Instead, we have to let the logarithm be part of the u. Then the dv is just x dx. V then becomes, let's see, add 1 to the power, multiply by the reciprocal of the power, that's 1/2 x squared. Now we got to stick the 5 somewhere. You could actually factor the 5 out front, but then you have to remember to distribute it down here, and I find that has a tendency to cause students more headache than it's worth. So I try to let the 5 either be part of the u or the dv. It doesn't really matter. I usually prefer to put it with the u. So I like to get the dv just like it is without having to mess with the constant. Just like I need it without having to mess with the constants. And then any extra constants I have, I stick them over here. Okay? So the derivative of 5 ln of x is 5 times the derivative of ln of x. It's just 1 over x. And then we have our dx. So du is 5 over x dx. Okay, so now we have u, we have dv. We computed du and dv, and v, rather. And if we group this together, the 5 ln of x, we see it becomes u. The x times the dx becomes dv. And we have the integral, or antiderivative, of u dv. Well, according to the parts rule, that says the answer should be uv minus the integral of v to u. Substituting back in, u times v is 5 ln of x times 1/2 x squared, minus the integral of v to u. So that's minus the integral of, let's see, the v was, here it is, 1/2 x squared. The du is 5 over x dx. Now look what happens when you have these situations. The nice thing about the logarithm is when you do a derivative, you get no more logarithms or exponentials. You get just a 1 over x. In this case, we got the 5 there as well. But that's going to work out nicely to actually end up lowering this power here. So an x squared divided by x is just x. 5 times 1/2 is 5/2, which I brought out front. I just did a little reordering here. 5 times 1/2 is 5/2, and I decided to put the x squared in front, then the ln of x. It's all multiplication here. And then, hey, sure enough, we got an integral here that we know how to do, something we know how to take the antiderivative of. That's just 1/2 x squared. Multiplying these together, that's 5/4 x squared there. The last integral sign disappeared, so don't forget your plus c. Now, actually, what I did here is I actually factored out a 5/4, and they both have an x squared, so I factored that out. Now, if you look at that, this is exactly 5/4 x squared with a minus 1 here. So when I factor out a 5/4 x squared, all I'm left with here is -1. And I'm dividing this by this, I ended up with 2. The x squared is gone, and I get ln of x. Let's just double check by distributing back out. 5/4 times 2 is 5/2 x squared, and then ln of x. And here, 5/4 times the -1 times x squared is -5/4 x squared, which is what this is as well. So there we get it. The plus c is outside of this factoring. It's not inside the parentheses there. So be sure you notice that as well. So that's outside, and we have what we're after here. Okay. Let's do one more. Just got one more of these. This one here, we end up having to do integration by parts twice. It's a lot like the first example we looked at. Here we have a polynomial, x squared, and we have an exponential, e to the 3x. So you let u, I'll call it u1, be x squared. We'll see about the 1/3 in a minute. dv becomes e to the 3x, and then if I make a 3dx, that's e to the w dw. Now, if I need the 3 with that to be part of the dv, then I need to balance that with the 1/3, which I make part of the u. All right, that'll work out. Let's see, dv1 is e to the w dw, e to the 3x 3dx. So v1 is just e to the w, e to the 3x. Here we just take a derivative. 2 times 1/3 is 2/3. X goes down to power 1, and then of course we always have our dx as part of our du. So this is u1, this is du1, dv1, v1. So with that grouping here, we have a product of two things, our two parts. The first part is u, 1/3 x squared is u1 here. The second part is v1, dv actually. So this is dv1. And so the integral of u dv is uv minus the integral of v du. That's the parts rule. And so we end up multiplying these two together, 1/2 x squared times e to the 3x minus the antiderivative of, and then let's see, this is v du. So where's v? That's right here. And du is these two. So e to the x times 2/3 x. Now, when we look at this, problem is this still has that x there. So we can actually do parts again. Now I brought the negative inside here, made that a plus. Now again, we would like to have the same setup for dv again. So we'd like dv2 to be the same as dv1, e to the 3x 3dx. So we're going to group that together. Now to get the coefficient to work out right here, the constant part, if I put this 3 here, if I put a 3 here, I got to balance with the 1/3. The 1/3 times the negative times the 2/3 times that -1 is -2/9. So that makes -2/9 x, this part, be the u. So that's u2. So dv2 is e to the 3x 3dx, just like it was before. And so v2 is the same as v1, e to the 3x. u2 is slightly different. In fact, most importantly, it's first power this time. So when I take a derivative, I get a constant times my dx. Well, that's nice because this time, by putting the plus here, I don't have to worry about any distributing now. So I still got this first term, which was my original u1 v1. It's just kind of coming down here for the ride. So 1/3 x squared e to the 3x. And then what I get is u2 v2 minus the integral of v2 du. uv minus the integral of v du. So uv is multiply these two. That's -2/9 x times e to the 3x right there. And then v2 was the e to the 3x, and the du is -2/9 dx. Be sure you put parentheses here so you don't think of this as subtraction right here. Now if I take the -2/9 and put it with the -1 out front, that becomes positive. I need to also put a 3 here and a 1/3 out. So put a 1/3 with this, which becomes 2/27. So take this, and just to be sure you got it here, multiply 2 27ths times 3, and notice that's the same as, it's actually positive 2/9, but these two negatives here multiply together to make a positive 2/9 as well. So that's legit. And now with that grouping, we have e to the w dw, which is e to the w, so that's just e to the 3x times the 2 27ths, and now we've got our plus c. Notice all of these have e to the 3x. I factor that out. And actually, I want to get rid of the fractions as well. Kind of like getting a common denominator. So find the common denominator here. 3, 9, and 27 is 27. So factor out a 1/27th, which means you're just multiplying all these guys by 27th here. So 27 divided by 3 is 9. 27 over 9 is 3 times negative 2 is negative 6. The 27s cancel here, giving you 2. And either 3x's are gone, but the x squared and the x are still there, here and here. So let's just double check with distributing. 1/27 times 9 is 1/3, x squared e to the 3x. 1/27 times negative 6 is negative 2/9. We have the x and e to the 3x. Plus 2 27ths e to the 3x. And then, of course, our plus c is outside all that. And so there we did it. And what would you do if this was x to the 15th e to the 3x? Well, you might have to do this 15 times, but you could do integration by parts over and over and over again, and eventually you can get it to work out with the same basic approach that we did here. Let's stop there for the moment, and we'll come back in our next example and look at a basic table of integrals, and then we'll look at another topic called improper integrals after that.